Yeah, so yeah, happy to be able to present this paper to you on level-dependent lambda calculus and gradual typing, as Jonas just said. So this is in collaboration with my postdoc Wei Li and my student Fabian and some younger version of myself, I guess. Let me first tell you what I mean when I say label-dependent lambda calculus. Well, it's a dependently typed functional language. So you have like the usual dependent function and dependent pair constructs. So it's a lightweight calculus. It doesn't have like full dependency, so you can put any type there and expect it to write a function that is dependent on it. And what's also different to your usual dependently typed language is that this is entirely inside of call by value. So the whole thing is not geared towards specification or proving things, but it's geared at programming, doing programming with interesting types. Right. So what can you depend on in this calculus? As the name says, label dependent. So what's a label? A label is, in some sense, an enumeration type. In this case, you don't have to declare enumeration types before the fact, but you just have some set of labels from which you can draw, and you can mix and match in every way you want. Then the elimination construct, label elimination, that's a case, and it works as you would expect. So here the X is the expression that you can scrutinize, and then you have cases for as many labels as you wish. And depending on what you're using, that determines the type you can put here, and so on. So labels are first-class values, like symbols. I Maybe some of you are familiar with Pi Sigma. That's a paper by Thorsten Altenkirch and Andres Le and someone else who escapes me right now. And after the fact, I found out that they are also using a quite similar setup in order to declare a minimalistic dependently typed language. Right. There should be more. Right. And what's also an interesting and complicating aspect due to label types, subsetting of label types actually induces subtyping, a subtyping relation in the sort of obvious way, and it's also propagated in the standard way to some types and product types using the usual rules that are there for dependent types. Let me mainly proceed by examples, and closer to the end, I will show you some disgusting typing rules, but only like 2 or 3 of them, so don't worry about that. Well, what can you do in such a language? So, for example, you can use the pi and sigma types in order to implement records and write functions on top of them. Yeah, so, for example, here this is a data type for person, and essentially you can view these labels here as field names for the record. And then here this case distinguishes on the record that you're on the field that you're selecting, and then you can have different types. All right, mind you, so this is an expression that lives on the type level. So the case, and that's where the label dependency comes from, can be used at the expression level as well as on the type level. So you can have type declarations like this here. And then field access is just function application, and the types just work out in the way you expect. And record subtyping is then, so if you have these subset types, if you have subtyping generated by subsets of labels, then the subtyping for these funny function types actually work like record subtyping. So it fits really in the way that you would expect. Right, and then you can write functions like this here, where you see some dependent typing. So essentially, you have a function that takes such a label, it takes a person, and then you have the case again. Only that in each of the different cases, depending on the label, you get the X the argument here gets a different type, and then you can just invoke functions according to that type. Right. But as you can see already, writing out these types in so much detail is pretty tedious and it's a bit repetitive. Yeah? So you would expect that this is already sufficient to see what kinds of fields are used here. And that's one place where you might want to use gradual typing. So that's one aspect of gradual typing. I think I've here. So what you do is, very roughly, you extend the system by a dynamic type, and the idea then is that the dynamic type is sort of compatible with pretty much any other type. But then there's an additional discipline so that the transition between precise types and less precise types, which involve the dynamic type, is made sort of seamless. So, of course, you can now write programs that would give rise to runtime failures. In order to avoid those runtime failures, gradual typing has a discipline that automatically inserts the necessary runtime checks so that you have a guarantee that, well, either your program is running entirely in the static part, in which case no runtime check can happen, no runtime failure can happen. Otherwise, you don't get failures, but instead of failures, the runtime checks inserted by the gradual typing will prevent you from misinterpreting data. And that's actually one of the uses, sorry, of gradual typing, that in case that the typing is really tedious and maybe you want to quickly prototype something, you can use the dynamic type and then figure out, make it more precise later on when your program has progressed. So that's one of those things. And and that's why we're interested in adding such a gradual type to a dependently typed system, because if you've done programming with dependently typed systems, then it's sometimes really a pain to figure out those types in advance. And sometimes there's enough context, like in this case here, to have the type system figure it out. For example, here, as I said 2 slides back, essentially here this case construction has enough information for the type checker to figure out that the only thing, even if I give it type dynamic, that the only thing I can meaningfully pass in here must be one of those labels. And indeed, if I try to do a field access on a non-existing label, so remember I can mix and match labels, no problems, then this already fails to type check, because there's enough information propagated inside of our type checker to see that even though the type is announced as star, it's not acceptable. This fits in with the ideas of gradual typing, where you are allowed, the type checker is allowed to reject programs that are doomed to fail anyway. And that's such a case. Whereas if you apply such a person to the name label, then you correctly get the name field extracted. Then also the printing can be done simpler. So I can also just, I don't have to enumerate the labels here. I can just say star and then invoke that and all that type checks without any issues. And also runs without any issues. Although here things are a little bit more indirect. So at this point here, field to string. So here you're accepting something of type dynamic. And at that point, when at the point of the function call of field to string, it's not yet clear to the type checker that you're going to use that as a field access to a function of this type. So this one will type check. So this is a label type. A label type is subsumed by the dynamic type. But then when it actually tries to do the casing here, then there will be a runtime check which checks, oh, is it actually one of name age flag, and that check will actually fail. Yeah, so that's what's happening under the hood, as we will see on one of the next slides. Let me go to the next slide. What's going to happen underneath? So first, we start out with some base language. That's like the language that I showed you on the first slide. So that's a lambda calculus. You have these labels, and you have the pi and sigma types that we had on the first slide. And then you have the usual call by value operational semantics. And we designed a bidirectional type system, which gives more or less immediately rise to an algorithm. So that is all decidable and whatnot. Okay, then what I showed you next is the gradual language. So that is essentially this calculus, and on top we have this star type, and the star type is kind of seamlessly included. So there is a notion which is called consistent subtyping, or let's say gradual consistent subtyping, and that tells you essentially if I'm expecting something of type dynamic, then I can also pass a label, or if I expect something of type dynamic, I can also pass a function or whatnot. So in this case, in the gradual language, as I just tried to tell you, the star type, the dynamic type, is compatible with any other type. And then the technical part is, so you have an extended bidirectional type system, but the translation, the semantics is actually given by translation. Now that's also a common thing in gradual languages. So you have this here, what I call gradual language. Some people call it external language. That's the surface language in which people are actually supposed to write their programs. But this language as itself, it has no semantics. So the semantics is only given by the translation, and the translation gives rise to the third language. So that's a bit annoying by these in these frameworks. You always have to deal with 3 languages at once. Sorry about that. So the third language is the cast language. So the cast language is actually much closer to the base language. So it also has the same type structure. It adds the dynamic type, but then the dynamic type is not compatible with any other type. So in order to get into or out of the dynamic type, you have to explicitly write down casts. And those casts have to follow a certain discipline, which is technical, so I won't go so much into it. This has, again, an operational semantics. It's the semantics of the original base language is 100% included. On top of that, you have the stuff that is dealing with casts. If we were talking about simply typed lambda calculus, then what happens at this cast level is not that difficult. So here in this system, and also in system where you deal with polymorphism, the cast involves significant effort to deal with. And then the actual technical execution, like bidirectional type system, that's similar. So that's an extension of the previous one. All right, let's have a look. So we're getting to the part where, so if you're not technically minded, you may take a nap or something. I'm just showing you a little bit of the technical stuff below. So bidirectional typing means you have 2 different typing judgments. One which takes a term and an environment and synthesizes the type of the term. So the synthesized stuff, the output, I tried to print that in green. I think I did that also in the paper. And actually, I think it didn't use green so that people who are red-green blind have a chance to distinguish. And then algorithmic type checking just takes input and just says yes or no if it's acceptable or not. And these judgments are mutually recursive, and that's quite standard. All right, so I just picked some highlights. So many of the rules that you'll find in the paper are standard. So I'm trying to point you to places where you might find some interesting stuff. So one thing that we have in the system, which I haven't really seen in other systems, but I'm happy to get pointers to work like that. In in call by name systems, so in the usual dependency type systems, you just have one typing rule to deal with the sigma type, and it looks somewhat like that. So this is the algorithmic version. So here I have such a dependent pair, and the idea is, of course, if I say x colon a is m in n, then essentially I would like x to occur in n. In call by name, that's not so much of an issue. In call by value, it is actually an issue, because the point is what happens in this situation once you're at this point here. So once you've reduced the first component to a value. So what do you do now? Now, because the n here is allowed to refer to this value of x, right? In call by name, you could just say, okay, well, you wouldn't even reduce that to a value, right? So if you have a dependent pair, you would say, okay, fine, this is a value. I'm not touching the components. In call by value, you don't have that choice, so you need to evaluate it. And then you're at this point, you've got the second component. Unfortunately, the x appears in that, so you can't evaluate it, or you have to do things like evaluate with free variables. I mean, like normalization, which also opens a whole bit of worms. So we decided actually to equip the system with two kinds of products. So once the dependent product here is sufficiently evaluated, then it turns into a non-dependent pair. And the trick that makes the transition is essentially this reduction rule. So once the first component is sufficiently known, well, then I'm getting rid of the occurrences of x in the second component by substitution. And you can show that this is type preserving. So from this rule to that rule, and so you're in business, and you can completely evaluate your pairs, and everything is nice, and you can keep it. So this rule is very close to the standard rule that you would expect. The trick here is really this extra rule, and it avoids the whole business of a reduction with free variables in it. All right. So another thing that is specific to the system is that you can that you're using the case construct, which is on the type level, it's a large elimination. But this is the type level. No, this is the value level construct. So you're using actually the information that you gain from inspecting here the header, the x. You use that information in order to specialize your types and so on. So what happens is to type check the case here, I first synthesize the type of x. And if that x here has a singleton type, which means it's either a constant or it's a variable, of which I know that it must be bound to a constant somewhere in the context, then I'm just type checking one of those cases. And the others can contain whatever they want to contain. Now the question is, of course, how do I get to variables here that have a singleton type? Well, also by the case here. So if I get to the point where the type here that I'm scrutinizing is sufficiently unknown, so essentially what this says, so where is x? So x is some type D. D is a subtype of the set of labels that I'm expecting here. So L here is the set of labels that I'm casing on. This should better be a subtype, but it's not yet a singleton type. If it was a singleton type, I could do this rule, and I'm done. In this case, I'm picking up here the set of labels that could be contained in this type D, and then I'm essentially specializing the choice here by refining the type of x. So in the case where I'm looking at NL, I'm specializing x to the singleton type L of type D. It must be one of those, because the case just checked for it, right? So therefore, it's semantically okay to refine the type in the environment to this one here, because in that branch of the case, I know that. And now I have such a variable that's bound to a singleton type, and then if it's used again, I know about it, and you can reuse that And that happens on the type level as well as on the value level. And this is the judgment for the value level. And that gives rise to lots of complications. If, in particular, if you're implementing it, it's a bit nasty to do that. Right, and what I'm not showing you because it's more involved, but feel free to check it out in the paper. The same trick also works in the gradual typing. In that case, D here can be the dynamic type, but nevertheless, you can still refine the type in a meaningful way, so that yeah, I won't go further into that. But the same trick also works in the dynamic setting. So I always have to click several times here. All right. Now, last glance at casts. So I said before, in simply typed settings, dealing with the cast is not much of a problem. But here, it turns out that if you have a cast, before you can execute the cast, A here may be a type that contains variables, right? So it may contain one of those case constructs, and therefore, before I can cast anything, I need to reduce the type. I mean, what would you expect in a dependency type system, right? I mean, you have to do reductions in types. Since here in the cast you have types, you have to do reductions as well before you can reduce. So that's what's happening. So types can contain redexes, and you have to reduce them to a head normal form. If they are in head normal form, then you can do the, let's say, the usual things like factorization. So if you have a normal form to the left, then you can expect the normal form. You find out the ground type below it. Yeah, the ground type is for a function. The ground type is a function from star to star. So once this is sufficiently evaluated, then you can see which ground type it is, and then you factorize it so that you have one cast that maps the normal form to the ground type, and then the ground type to star. So that's a known thing, and then you're in distance. And this rule here, without the normalization, that's just a normal thing. Now, and what are ground types? Ground types are essentially normal forms, so they don't contain any cases. They just tell you, well, I'm a primitive type, or I'm a function from star to star. I'm a pair with with dynamic components, and so on. So then you're back to familiar ground. This is really amazing. Okay, so what did we do in terms of meta theory? So we proved the type soundness. Then you have I only showed you the stuff for the typing algorithm, but there's also a declarative specification, and that's sound incomplete with respect to the algorithm. Then we proved static and dynamic gradual guarantees, which are the usual technical results that you prove in this context. So what did we do? So we designed this lightweight, dependently typed lambda calculus with label dependency, with subtyping, and with the special treatment of pairs. Maybe it's not so lightweight after all. Then we looked at the gradual extension of the calculus. We developed the meta theory. Type checking is decidable. There's an artifact, so there's an implementation. You can play with all that. Some part of the meta theory is mechanized. That's also, that's this description of the artifact. That's also in the artifact. Meanwhile, we have more mechanized, which we didn't get around to back then. And there's also an implementation of the type checker. Meanwhile, there's also an interpreter, so you can also run those programs. So what else? Future work. So in case you watched the video last year, so I didn't. This slide is not in the video. Future work. So one thing that was on my wish list for a long time is generalizing that kind of approach from labels to general inductive types. So we are in the process of finishing that. The interesting thing is, that here we still have just a case construct to do large elimination, but in addition, to deal with the induction, we have a recursion operator. So that and the trick is, of course, well, you want it to terminate. So we have a size-driven termination argument for that. Yeah, so the recursion is restricted in a way that it can only be invoked on subterms. Yeah, so originally, and in another system, we considered to have dedicated recursors for each inductive type, but it's just too tedious to program with those recursors. So in this case, we went for a named lambda and essentially like rec fx, something like that. Right, the implementation of that type checker is ongoing, and we hope to have a look at the gradual aspect once we've finished that. So that's like the inductive data type equivalent of LDLC. So that's what we have currently, and the next thing to extend is the gradual stuff. Well, and with that, thank you for your attention.
We have time for a few questions.
You need the microphone, right?
Yeah, we would need to move around the mic.
Yeah.
You can maybe answer from
Yeah, I use that. Sorry about that. No, don't worry.
Thank you for the talk. One of the earlier slides, I must say I was a tiny bit disappointed in one of the examples where you had you had a function where the first type was the star. Very early, yeah. Oh wait, maybe it's here. Yeah, this one. So in the very last example, I would think that, okay, you put the foo argument, that's fine that it type checks, but once you put the p argument, I thought it would already fail to type check. Because once you put p, you would know that the label foo isn't there.
Okay. Yeah, but the thing is, at that level, you know that this is a star, and you know this has this type pi star to this case. So it's not yet clear that that you're going to apply this function to this argument.
Okay,
you don't see it here. Yeah? As soon as this becomes obvious, then like here, oops. Yeah, like here it's obvious. Yeah, so you have the application to foo, and then the type checker can find it out.
Okay. Yeah, I see the difference. Okay, thank you.
We have time for one more question.
I have to say, initially I was surprised that it's rejecting that, but
yeah, the other case
probably a very stupid question, but how does this differ from record types that could be dependent?
Oh, so this is one possibility of modeling record types, but you can do a lot of other stuff. I mean, so you can do sigma types. You can use sigma types and roll your own dynamic version of algebraic data types. But I mean, it's totally up to you what you do with this label dependency. It's just one example. So in the paper there are other examples of applications. Of course, it gets more useful once you have general inductive types. Yeah, but that's quite an extra effort to do that.
All right. Thanks, Peter. Again.
Yeah, thank you for the questions.